Hello everyone and welcome to Engineering Statics. Today what we're going to do is just do a quick little example of solving for the vector components of a force. In this problem we have a tower that is 80 meters tall, 40 meters from the connection point of a cable to the top of the tower. This tower is up here, it has two tension cables. The force of one of these tension cables, and we'll assume it's symmetric, so the force of both of these tension cables is 900 newtons. You may have seen vectors denoted in your textbook as bold. What I'm going to do to denote a vector is just underline the letter, and that's basically a bolded letter. For this example, I'm going to work at two different ways for you. Both of them are kind of high school level trigonometry or similar triangles, so it shouldn't be too difficult. But I want to show how you can break this into components of x and y. So what I'm going to do to this picture right here is basically it's in a free body diagram form right now, so that's okay. But I'm going to add on an axis system right here that we didn't have before. So we'll call this y and this direction x, so that we have this all defined in a way that makes sense to us. Okay, so the first thing we want to do is we have this force acting at an angle, and we have two sides of a triangle. The first thing you normally want to do in this situation is find some angle theta up here. So what we're going to do is just go ahead and find that angle, and we'll find out that theta is equal to the arctangent of 40 over 80, which will end up equaling 26.6 degrees. Pretty easy. Hopefully you guys all are familiar with that. Okay, from there, what we have to do is break this force into its x and y components. And in order to do that, what I'm going to do is I'm going to come over here, I'm going to make 2 points to denote the force function, and we'll just go F like this. And I want to draw this so that you guys can really see. So if you've got an axis like this of y and x, then to get the y component and the x component, you basically make a triangle out of the vector. So this will be, y will be your j component, and this will be your I component. Well, you have a magnitude of 900 newtons for this, and you have the angle theta. So this again is just a trigonometric problem to get these two other sides right here. So the total force, F, we know is 900 newtons, is going to equal the magnitude of F sine of alpha, or no, not alpha, theta, sorry. Theta, and that's going to be in the I direction. So we're basically taking the sine of this angle and the magnitude of this, which is 900 newtons. Sorry, I should have denoted that up here. This F, the magnitude of F, is 900 newtons. Like that. These bars denote magnitude, which basically means the hypotenuse of a triangle. Okay, so sine of that minus F of cosine of theta. And that is in terms of J. Okay, now, you guys may have wondered about this minus. If you aren't familiar with the minus, this is dependent on how we denoted this axis system, because you'll see that this vector is made up of a vector in the j direction going that direction, and a vector in the I direction going to the right. Since this is going down, it's going opposite to the axis system that we set up right here. So it's going opposite to the direction of the axis y, so it's a negative value. So when you're going to find this y value or j value, you have to say it's negative. So how you assume your axes, or how the axes are set up in the problem, is very important to realize, because since vectors have a direction, if it is opposite to your axis system, it is negative. And the x is within the same direction as the axis system, so it is positive. Something to remember right there if you haven't been introduced to that already. Okay, so now adding in all of these values, we end up with 900 sine of the angle that we just got, 26.6 degrees in the I direction, minus 900 cosine of 26.6 degrees in the j direction. And this is all going to be in newtons because the force is in newtons. And if you solve that out, you'll end up with 402 I minus 805 J newtons. Always keep your units as you go through these. So we have a component in the x direction of I of 402 newtons, forcing in the x direction, and then 805 newtons forcing downwards in the y direction, which makes sense. So you can always kind of reality check yourself on these when you're thinking about it. If you look back at your picture and you look at these forces, you realize that, oh, negative. Negative is against the y up here in the picture, so it has to be pulling down. And these are tension cables, so yes, they are pulling down. So a reality check. If for some reason it was positive, that means it was pulling up, which can't possibly happen in this situation. So your signs are really, really important in statics. Make sure you always keep track of those. Okay, so that's one way to do it. The second way to do it is to calculate basically this distance right here, and then use similar triangles in order to solve it out. So I'll redraw this picture here real quick. We got the side of the tower. This is 80 meters, and this is 40 meters. 40 meters. So you want to find this side right here. We know that it's a right triangle. You could find that angle again and solve from there, but since you've got two sides right here, it's just easier to use Pythagoras' theorem. 40 squared plus 80 squared, 80 squared, square root of Pythagoras' theorem, a squared plus b squared, square root, is equal to 89.4 meters. So then this side is equal to 89.4 meters. Now we have a triangle that's all set up. And now the forces, this force F up here, will have the same triangle system, will be a similar triangle in vector forces as the actual physical measurement of the system. So what you can do is you can say the magnitude of the force in x, or the distance in x, with respect to the force in x by the vector with respect to the actual force, which we'll underline right here, is the same. So if we create a vector triangle right here so you guys can see what I said earlier. I'm going to redraw this one more time. It's not a very good triangle. This triangle is exactly the same as the forces acting on it, just like this. We've got a right triangle. Whereas this 80 corresponds to this magnitude of force, this 89 is the same as this magnitude of force. So you can use ratios to determine what the components are of the force by using the ratios found by these distances. So if we have the force in x, this force right here, we'll call this f of x, this f of y. You do the ratio of that with respect to the hypotenuse. This is f, large F, the magnitude that we were given. We know the distances are 40 meters all over 89.4 meters. And we know that F is equal to 900 newtons. So you can basically solve for f of x that way. And then in the same way, you can do f of y, the magnitude of f of y, all over large F, is equal to the ratio of the y distance to the hypotenuse, which is equal to 80 meters all over 89.4 meters. Just like that. And you know this is 900 meters, newtons, so you can solve for f of y. And there are your two components. Now here's the thing though. You have to realize, just like in the previous half of this example, what direction these vectors are going, because this gives you the magnitude of the vectors, the total power, the total amount of force that they have, but it doesn't tell you the direction. So that's something you have to assume. So in order to get the final force, you have to get 40 over 89.4 times 900 newtons. I, which is just solving out this equation right here and plugging it in down here, minus, we have to assume it's minus because we know that the y vector is pointing down, which is opposite to the axis system that we set up where y is pointing up and x is to the right. That was just inherent in the problem. So you have to realize that this is a negative right here, which is then equal to 80 over 89.4 times 900 newtons in the j direction. And if you solve that out, you will end up with 402 I minus 805 J newtons, which is exactly what we had up here. So this is your answer. This is the magnitude. This is the component representation of the force vector that we knew was 900 newtons from how the problem was set up. So you can either do it trigonometrically, where you use sines and cosines, or you can use similar triangles. The most important thing to remember is that you know where the negative signs are, and these are determined by how the vectors point with respect to your axis system. If they go with your axis system, then they're positive. If they go against your axis system, then they're negative. That's incredibly important. It will be a big problem for a lot of people as they go through statics.